To make your smartphone faster, engineers they don't need better physical tweezers anymore. They actually need an abstract math trick from a textbook to stop a microscopic traffic jam.
Yeah, it's a completely different way of thinking about the problem.
Because usually when you look at that incredibly thin laptop on your desk, there is this underlying assumption you make, right? We just assume that we keep shrinking things. Like, we assume chip designers are sitting in a clean room somewhere, just endlessly making the wires smaller and smaller so your devices can get faster without, melting a hole in your hands.
Right. I call that the infinite miniaturization myth. People find it really comforting to think progress is just a straight downward sloping line on a graph. You just make the components smaller and everything just gets better forever.
But then you step into the actual physical reality of modern silicon die design, and that assumption completely shatters. I mean, we are hitting a literal physical wall here. You can't just keep shrinking the wiring, because at a certain point, the physics of electricity just flat out refuse to cooperate.
They do. The physics become your enemy.
And that brings us to our mission for this deep dive. We are looking at a 2026 technical briefing by Hua-Xing Look, and it's titled Scalable Interconnection Networks via Cyclic Quorums. Now, if you are someone who loves those sudden aha moments, or you just wonder how the technology in your pocket actually functions on an atomic level, this is for you. We are going to explore how pure abstract math rescues physical engineering from an impending bottleneck.
Exactly. And we aren't just going to look at the wiring of computer chips. We need to look at why this specific mathematical approach is revolutionary and how it fundamentally alters the future of computing architecture. Because right now, the industry is facing an absolute nightmare.
Okay, let's unpack this, starting with the core problem. Before we can appreciate the brilliant mathematical solution, we really have to understand the physical nightmare that is currently keeping chip designers awake at night. In the briefing, it's referred to as the crossbar paradox.
Right. So at its foundation, a microchip is really just a vast network of connections. You have a massive set of inputs, and let's call that group N. And they all need to communicate with a shared set of outputs, which we will call M.
Okay, N and M. Got it.
Yeah. And traditionally, designers connect them using what's called a naive crossbar approach. So picture a brute force grid. Every single input has a potential intersection with every single output.
Right, and Look gives us some very sobering numbers to illustrate what that actually looks like on the silicon. Let's say you have a relatively small block, like 100 inputs and 24 outputs. A naive crossbar for that block requires 2,400 physical junctions. And in chip design, those junctions are called vias.
Vias, yes.
They are essentially tiny vertical metal tunnels connecting different layers of the chip. So 2,400 vias, that doesn't sound completely unmanageable, does it?
I mean, it doesn't, until you realize that the naive crossbar falls into a terrifying mathematical trap, which is quadratic scaling. When you try to scale up that design to meet the demands of modern artificial intelligence or, high-performance computing, the math just explodes.
Totally explodes.
Yeah, by the time you need 1,000 inputs to connect to 256 outputs, you suddenly need 262,144 junctions.
Over 250,000 microscopic vertical tunnels just to get signals from point A to point B. The briefing is extremely clear about this. At the 7-nanometer scale and below, packing that many vias into that tiny of a footprint is physically impossible. Think of it like trying to build a futuristic city where every single house has a dedicated private paved road connecting it directly to every single grocery store.
That is a great way to visualize it.
Right. Very quickly, the entire city is just asphalt. There is no room for buildings and nobody can move.
If we connect this to the bigger picture, it is not just a space issue. In the world of electronic design automation, or EDA, which is the software used to lay out these chips, this density wall triggers what the briefing defines as the 4 structural penalties.
4 penalties. Okay, what's the first one?
The first one is routing congestion. The software itself literally struggles to find a path through this maze of vias. Heavy local metal crowding blocks the tracks, meaning signals have to take massive detours just to find an open lane.
Like getting off the highway because of a traffic jam and getting lost in the suburbs.
Exactly. Then there's the second penalty, which sounds a bit like a sci-fi villain, parasitic dominance.
It does sound ominous, but what does it mean physically? Wait, parasitic.
Yeah, physically, it is a massive problem.
Right.
At a microscopic scale, wires aren't just empty pipes, right? They have electrical fields. So when you pack 250,000 metal wires that tightly together, those fields bleed into each other. You get massive wiring capacitance and resistance.
Oh.
Yeah, the wires act like sponges, soaking up the electrical signal and slowing it down. This causes RC delay violations, which stands for resistance and capacitance delays. The physical interference of all that metal means the crossbar itself becomes a critical path. It fundamentally limits the speed and reliability of the entire chip.
And if the congestion and the signal bleeding wasn't enough, we hit the third penalty, asymmetry chaos.
Yes, asymmetry chaos.
Because this brute force grid is so sprawling and dense, the physical path that input 0 takes to reach an output is radically different from the path that input 99 takes. They experience totally different levels of resistance and capacitance, which leads to severe signal skew. The signals just don't arrive when they are mathematically supposed to arrive.
Right, which breaks the timing of the whole system. And finally, the fourth penalty is no modularity. Because every dense crossbar turns into this sprawling, chaotic mess of custom routing just to avoid all the congestion, you can't reuse a design.
There's no copy-paste.
There is no stamp and repeat. Every single time a designer needs a dense crossbar for a new chip, they are starting from scratch, painstakingly routing a custom layout. It is incredibly inefficient.
So if we can't fit more roads into our asphalt city, and the traffic is moving at a crawl because of parasitic interference and, cars are arriving at totally random times, we just can't build more. The only option left is to radically change the map.
Precisely. We need a new map.
And this leads directly to the central thesis of the briefing, a concept called cyclic quorum systems.
A quorum system, in this context, is a collection of overlapping subsets that are mapped onto a cyclic mathematical group.
I'll be honest, that sounds incredibly abstract. Let's ground this for a second. Instead of a random, sprawling grid where every wire crosses every other wire, the inputs follow a single relative geometric footprint. And the specific mathematical structure the briefing focuses on to achieve this is an order 3 projective plane, which the author denotes as 13, 4, 1. Break down those numbers for us. What do 13, 4, and 1 actually mean?
Let's visualize it. In projective geometry, an order 3 projective plane consists of 13 total points and 13 total lines. That's our 13 by 13 matrix. 13 inputs, 13 outputs.
Okay, so that's the 13.
Right. The number 4 means that every single line contains exactly 4 points. And the number 1, and this is the most important part, means that any two lines will intersect at exactly 1 point. No more, no less.
So if we built a naive brute force crossbar for a 13 by 13 grid, we would need 169 vias, right? Every row intersecting every column.
Exactly. 13 times 13.
But with projective geometry, we use something called a Singer difference set. And the set used for this specific 13 by 13 grid is the numbers 0, 1, 3, and 9 modulo 13. Now, we need to explain modulo 13 because it is the absolute secret sauce here. Modulo is essentially a clock math.
Yeah, imagine a clock, but instead of 12 hours, it has 13 hours.
Right. So if you are at 10 o'clock and you add 4 hours, you don't go to 14 o'clock, you wrap around past 13 and land on 1. That is modulo 13. Now let's look at the Singer difference set again. 0, 1, 3, and 9. If you take any two numbers in that set and subtract them using our 13-hour clock, something brilliant happens.
It really is beautiful math.
Yeah, 9 minus 0 is 9. 3 minus 1 is 2. 0 minus 1, well, if you step 1 hour backward from 0 on our 13-hour clock, you wrap around to 12. If you do this for every possible combination of that 4-number set, you get every single number from 1 to 12 exactly once.
All non-zero differences appear exactly one time. No repeats, no missing numbers. And what that means physically for our microchip is what the briefing calls the intersection property. Because of this perfect mathematical symmetry, you do not need 169 connections. You only need to place a via at the rows corresponding to those set numbers, row 0, row 1, and row 9.
So that means you only need 4 connections per column instead of 13. Think about that visually. Imagine weaving a basket. Instead of a dense, heavy grid where every thread crosses every single other thread, you weave a pattern where every thread crosses every other thread exactly once. It creates this beautiful, sparse, diagonal wave pattern across the silicon. You only need 52 total vias instead of 169. That is a massive 69% reduction in physical junctions.
It is a staggering efficiency gain.
Yeah.
You are freeing up an enormous amount of physical space on the die, drastically reducing the parasitic capacitance we talked about earlier.
Wait, stop. I have to push back here. If we are deleting nearly 70% of the connections, don't we lose the ability to actually route the signals? How does a signal get from A to B if the road is physically gone? I mean, if input A wants to talk to output B and we erase the via at that specific intersection to save space, the signal is just trapped.
What's fascinating here is that the mathematical property guarantees uniform connectivity. Every row sees the exact same electrical load. Remember how every number from 1 to 12 appeared exactly once when we subtracted the set? That property guarantees that the road isn't erased. It is just perfectly optimized. But you are absolutely correct that not all input-output pairs have a direct single-hop via anymore. We have moved from static math to the dynamic reality of chip operation. And this brings us to multi-hop routing.
Okay, so we are taking detours.
Exactly. Because of that one intersection property, remember the 1 in 13, 4, 1, any two inputs will always share at least one output. In computer science, we call this a connected bipartite graph.
A bipartite graph.
Yeah, it just means you have two distinct groups, inputs and outputs, and connections only flow between the two groups, never within the same group. Because of our different set, every single node in the input group is mathematically guaranteed to be connected to every other node through an intermediary in the output group.
The briefing highlights a larger design example to show how this works in practice, a block with 100 inputs and 23 outputs. In this sparse model, each input connects to only 6 out of the 23 outputs, so the vast majority of direct paths are gone. But because of the math you just described, the maximum travel distance, the diameter of this entire network, is just 2 hops.
Think of it like booking a flight. You want to go from a small airport in Maine to a small airport in Oregon. There is no direct flight. But the airline hub system guarantees you a single connecting flight that gets you to your destination. 2 hops.
My concern is speed, though. On a computer chip, a signal having to stop, ask the router for directions, figure out the connecting flight, and then fire again sounds like it would introduce a massive latency delay. And these chips need to operate in fractions of a nanosecond.
That would absolutely be the case if the chip were figuring out those directions on the fly while it was running. But it doesn't do that. This relies on an algorithm called breadth first search, or BFS.
Here's where it gets really interesting.
Yeah.
The routing software runs that BFS algorithm at design time.
Yes, exactly.
While the chip is still just a blueprint in the EDA software, the algorithm maps out all of these 2-hop paths. It explores the entire network, discovers every single required route, and then it hard codes those paths into a lookup table, LUT, right onto the silicon.
That distinction between design time and runtime is the crucial step. By doing the heavy computational lifting before the chip is even manufactured, the actual execution is practically instantaneous. In computer science, we say finding the route takes O of 1 runtime.
O1?
Yeah, for anyone not familiar with big O notation, O of 1 means constant time. It doesn't matter if there are 100 routes or a million routes, the time it takes to look up the answer is always exactly the same, and it is essentially 0 latency. It's the difference between navigating a maze while you're inside it versus having a map of the maze completely memorized before you even walk in. The chip just checks the table and fires the signal.
And the physical payoff is incredible. In that 100 by 23 model, a brute force dense crossbar would require 2,300 vias. By using the Cyclic Quorum and this 2-hop lookup table trick, the design only needs 600 vias.
That is a 74% reduction, from 2,300 down to just 600. You eliminate the routing congestion, you eliminate the parasitic dominance, and you achieve this without sacrificing any runtime performance because of the constant time lookup table.
We have officially solved the density wall. But looking at the Python demos included in the briefing, there is an obvious, messy, real-world problem here.
Always is in the real world.
Right. The math is incredibly elegant when we are dealing with a perfect 13 by 13 square. But engineering specs don't care about perfect mathematical symmetry. A client is going to demand a chip with 39 inputs and 13 outputs, or 41 inputs and 12 outputs. How does this fragile mathematical framework survive contact with weird non-square demands?
It survives through 3 very clever scaling strategies. Let's look at your first example, a spec demanding 39 inputs for 13 outputs. Because 39 is a clean multiple of 13, the designers use a strategy called horizontal tiling.
Right, you literally just take that 13 by 13 macro cell we built, the one with the sparse 52 vias, and you just copy paste it 3 times side by side. 3 blocks of 13 gives you your 39 inputs, and the total via count. 3 times 52 is 156. If you built a naive crossbar for 39 by 13, you would need 507 vias.
It scales effortlessly. But as you said, specs are rarely clean multiples. What if the design spec demands exactly 38 inputs?
The briefing says we use a strategy called truncation. You take that 39 input tiled design and you just slice off the final column. Column 38 is just deleted. But I have to ask, wait, slicing off a column in truncation feels a bit like a hack? Doesn't chopping off a piece ruin the elegant mathematical symmetry and electrical balance we just built?
I mean, it feels like a hack, but physically it's perfectly safe. Truncation works because the underlying macro cell design remains totally identical. Columns 0 through 37 still maintain the exact same electrical and crosstalk profiles they had before you made the cut. The via density stays exactly the same, 4 per column. The router software and the EDA tools completely loves this kind of predictability
Why do the tools love it so much?
because it allows for hard macro copy paste. You design one highly efficient column template and you stamp it across the floor plan as many times as you need. Every single column is electrically identical. And crucially, it allows for perfect metal layer stratification.
What does layer stratification mean in this context?
A microchip is like a multi-story parking garage. It has different vertical layers of metal wiring. With this predictable mathematical layout, we can organize the wiring hyper-efficiently. Short, dense, local wires can be relegated to the lower metal layers like M2 or M3. And the long, global connections, the pathways that need to span across the entire chip, can be placed on the upper, thicker layers like M6 or M7.
Oh, I see.
Yeah, those upper layers have much lower electrical resistance. Because the via placement is perfectly mathematically distributed, there are no congestion hotspots. The RC delays are perfectly matched across all channels, guaranteeing deterministic timing.
Meaning the chip behaves exactly the way the math predicted it would. No asymmetric chaos. But there is a third scaling challenge. What if the numbers are completely weird? What if the outputs are 12 and the inputs are 41? You can't tile 13s into 41 cleanly, and you can't just slice off pieces endlessly.
For those extremely mismatched dimensions, the Python scripts utilize coprime boundaries. This relies on the mathematical concept of the greatest common divisor, or GCD.
Let's slow down here, because this is where the math really bridges into the physical world. 41 and 12 are coprime. That means they don't share any common divisors other than the number 1. You can't divide them both by 2 or 3 or 4. Their GCD is 1. Why does that matter physically?
It matters because of how patterns wrap around a matrix. If they shared a divisor, say the number 2, a repeating pattern would loop back on itself prematurely. It would hit the same physical spots on the chip over and over, creating dense clusters of vias in some areas and leaving massive empty gaps in others.
But because their greatest common divisor is 1, a cyclic offset pattern will sweep perfectly across the entire matrix without ever hitting the same spot twice until it has covered every single required intersection uniformly.
Precisely. And the Python script in the briefing runs an exhaustive computational search to find the absolute perfect set of offsets for those specific coprime dimensions. In this case, for 41 by 12, the offset set is 0, 1, 4, and 6.
So the software applies that offset set, and because 41 and 12 are coprime, those offsets wrap around the modulo 12 outputs in a way that forms a flawlessly uniform diagonal wave across the die. It guarantees perfect row load balance and near zero variance.
Near zero variance is the holy grail here. It means every single part of the chip experiences the exact same electrical pressure. The software isn't just looking for an open path for a wire, it is exhaustively searching for the specific difference set that minimizes electrical variance. Low variance means matched delays, which means highly predictable timing.
And once again, the physical numbers are wild. This bizarre 41 by 12 design only requires 164 vias compared to 492 for a dense crossbar.
It's massive.
So what does this all mean? If we look at the key takeaways from Look's 2026 briefing, the main lesson is clear. We have to prioritize sparsity over density. By abandoning the naive brute force grid and utilizing cyclic block matrices based on projective geometry, chip designers can reduce via overhead by up to 80%. 80%. It's about replacing physical brute force with elegant deterministic math.
This raises an important question about how we approach engineering in the 21st century. For decades, Moore's law trained us to just pack things tighter, smaller, denser, more. But this briefing proves that we have hit the physical limits of more. We are learning that the only way to scale our technology into the future is not by building more roads, but by building smarter maps. The fundamental architecture itself must become mathematically optimized before a single piece of silicon is ever manufactured.
And it leaves you with a pretty wild final thought. If a deeply abstract mathematical concept, like order 3 projective planes and Singer difference sets, things that sound like they belong in a theoretical university classroom, can step in and perfectly optimize the microscopic physical infrastructure of a silicon chip to stop a traffic jam, what else is out there?
Right.
What other deeply abstract, seemingly theoretical mathematical concepts are just sitting in a textbook somewhere waiting to solve the macroscopic physical bottlenecks of our world? Could this exact kind of projective geometry perfectly optimize the routing of our national power grids, the logistics of our global supply chains, the wiring of future space stations? The next time you hold your miraculously thin smartphone and marvel at the fact that it isn't melting in your hand, don't thank microscopic tweezers. Thank abstract math for giving us a smarter map.
A smarter map indeed.